All right, in this video, we will be going over section 3.3. This section is about second derivative and curve sketching. If you remember, in the previous section, we were discussing the first derivative and curve sketching. This time, the second derivative comes into the play. Basically, the second derivative helps us to get a more detailed graph of a function. I want to start with this definition 3.9. This is how we formally define the concavity of a function. Here is the first part. F is concave up on the interval I if f prime is increasing on I, and f is concave down on the interval I if f prime is decreasing on that interval. Okay, let's provide two examples. Let's try to understand what this means geometrically. I want to provide an example for the part A first. Okay, if you look at this graph of y is equal to x squared, it looks like this. Okay, graph of y is equal to x squared looks like this, and here is the shape of a function which is concave up. Okay, as you can see here, we say that it is concave up if f prime is increasing. Is f prime increasing on this graph? As your x goes to right, as your x is getting bigger, is your f prime increasing? Well, you can see it. For example, what do you mean by, first of all, what do you mean by f prime? That is the slope of your function, slope of the tangent line to your function at a given point. For example, at this point, if you want to find f prime, that is the slope of the tangent to your f of x at this point. Okay, so slope of this tangent. And then if you go further to the right, and if you take a point somewhere here, and now if I draw a tangent, that tangent looks like this. As you can see, the slope of this tangent is smaller than the slope of this tangent. And if you go to further right and pick a point somewhere here, now if you draw a tangent to that point, tangent to your function, graph of the function at that point, slope of that tangent is positive. And if you go further, now your tangent would look like this. Slope of that tangent is bigger than slope of this tangent. Okay. Likewise, the slope of the tangent is increasing. That means your f prime is increasing on that interval. Actually, in this case, the interval is minus infinity to plus infinity, because this graph extends indefinitely. Okay. In that whole interval, your f prime is increasing. That can be seen by drawing tangents. You draw tangents at various points. Then when x is getting larger, the slope of the tangent is getting larger. That means f prime is increasing. Okay. Here is an example of a graph of a function which is concave down. Part B. I'm not going to give an explicit function for that. If you have a function like this, this function is concave down. Concave down. This is concave up. Again, you can, in a similar manner, you can argue that the slope of this function is decreasing on the interval minus infinity to plus infinity. Okay, I will leave it for you to justify that. Justify that the slope is decreasing, or your f prime is decreasing on minus infinity to plus infinity. All right, let's move on. Next, I want to go over this theorem. The second derivative determines concavity. Okay, we use second derivatives to determine concavity. Suppose f and f prime are differentiable on an interval I. If f double prime is positive on the interval I, then f is concave up on that interval. If f double prime is negative on the interval I, then f is concave down on that interval. Okay, here is the graph when your f double prime is positive on an interval. Okay, let's say this is your A, your interval. Okay, this is your B. Your interval I is A comma B. Okay, here is an example where your graph is concave up. Okay, and in that case, your f double prime is positive. Okay, if your f double prime is positive, then your graph f is concave up. And here is where your f double prime is negative. Here is a graph where your f double prime is negative. Okay, you should have a shape like this. This is the case when f double prime is positive. This is the case when f double prime is negative. If f double prime is negative, your graph should look like this. It should be a concave down function. If f double prime is positive, it should look like this. Your graph is concave up like this. Okay. All right. We are not going to prove this theorem. I will leave the proof as an exercise for you. Make sure that you read the proof in the book. Okay. All right. Let's move on to the next definition. Next, I want to define what we mean by inflection points of a function f. Okay. Inflection points of a function f are the points in the domain of f at which its concavity changes. Okay. Inflection points are the points where the concavity is changing. For example, think of a graph like this. Think of a graph like this. I have this point C. At this point C, let's say your graph is doing something like this. As you can see now, up to this point, your graph looks like this. It is concave down, right? I mean, this is the shape of a concave down shape. Remember, this is the concave down shape. That means this you have this part there, right? This part is the shape of a concave down function. Okay, this is concave down, but to the right of C, it is concave up. As you can see, the concavity is changing at this point from concave down to concave up. Okay, this kind of a point is called an inflection point. Okay, and notice that we know how to measure the concavity using f double prime from the previous part. If f double prime is positive, we know that function is concave up on that interval. If f double prime is negative, we know that the function is concave down in that interval. That means I can use f double prime, the sign chart for f double prime, to determine the inflection points. Inflection points are the points where f double prime changes the sign. Okay, positive to negative or negative to positive. Okay, so to find inflection points, what I need to do is I want to find the points where f double prime changes the sign. Okay. All right. Let's move on. Okay. Now let's work on this particular example. Okay. Use second derivatives to determine the intervals on which each functions that follow are concave up or concave down, then determine any inflection points. Again, notice that how do you determine the intervals where the function is concave up and where the function is concave down? We go to the theorem. This theorem tells you that if f double prime is positive, then the function is concave up on that interval. If f double prime is negative, then the function is concave down in that interval. Okay. All right. That's what we are going to use. We are going to check the sign of the second derivative, or in other words, we are going to construct a sign chart. Let's work on the first part. F of x is equal to x to the power 4. Now what I'm going to do is I'm going to find my second derivative. The first derivative is clearly 4x to the power 3. The second derivative of my function f of x is equal to 12x squared. Okay. Now I'm going to construct a sign chart for my second derivative. Why do I construct a sign chart? I want to identify where my second derivative is positive, where it is negative, in order to find out where my function is concave up, where my function is concave down. Okay, so let's construct a sign chart for my f double prime. This is f double prime. Construct a sign chart. I want to figure out where this function can change the sign. Okay, the point, first of all, I need to figure out the points where this function can change the sign if it does. Okay, so this function can change the sign only at its zeros because this function is defined everywhere and it is continuous everywhere. So this can change the sign only at its zeros if it does, of course. So zeros of this function is, you set your f double prime to 0, you get x is equal to 0. This is the only 0 of your f double prime. You mark that 0 on the number line. This is your 0. And then notice that to the left of 0, for any x value to the left of 0, your f double prime is positive, because if you plug in a negative number here, when you take the square, it is positive. So you get a positive sign in this region. And in this region also, clearly you get a positive sign. That means in this interval, on this interval minus infinity to 0, your function f is concave up because f double prime is positive. By our theorem, we know that if f double prime is positive on I, then my function is concave up. So let's write it here. F is concave up on minus infinity comma 0, and we have another interval where it is concave up, because in this interval also, if you look at this interval, there also my f double prime is positive. That means my function has to be concave up in that interval as well. 0 to infinity. These are the two intervals where my function is concave up. In fact, if you draw the graph of this function, y is equal to f of x, you can see that your graph would look like this if you draw it. Okay, as you can see, this graph is concave up in the left interval, minus infinity to 0, and it is concave up in the right interval as well, 0 to plus infinity. Okay, all right, that completes the first part. Let's move on to the second part. Here is the next function. Let me copy this function to the other side. Again, to determine in which interval my function is concave up and in which interval my function is concave down, what I'm going to do is I'm going to analyze the sign chart for g double prime of x, because then I can use the theorem that we discussed. If f double prime is positive, I know my function is concave up. If f double prime is negative, I know my function is concave down. So let's find the second derivative of this function. If you find g double prime of x for this function, you will get 6x. Okay, I will leave it for you to verify that. If you take the second derivative of this one, you should get 6x. Now we construct the sign chart for this function g double prime. Okay, notice that the 0 of g double prime, 0 of g double prime is x is equal to 0. It's clear. If you set this to 0, you get x is equal to 0. That's where your g double prime, that's the only point where your g double prime of x can change the sign if it does. Okay, there is no any other point because this is a polynomial. It is continuous everywhere. So it can change the sign only at its zeros if it does. Okay, so let me place that 0 here. Now I want to have the sign chart. Okay, notice that if I plug in a number to the left of 0 in my function g prime of g double prime of x, it's a negative number. Let me show you the work here for the first time. G double prime of, I'm picking a number to the left of 0, g double prime of say minus 1. That is equal to 6 times minus 1, which is minus 6. It is a negative number. That means this sign is positive. To the left of 0, your g double prime is positive. Similarly, you pick a number from the right hand side of 0 and plug in that in the function g double prime. let's say 1. This is equal to plus 6. It's a positive number. So, oh, pardon me, this number should be, this sign should be negative. This is negative and this is positive. Okay. Now I have the sign chart for g double prime of x. Okay. Okay. Now I can use the previous theorem to determine where my function g is concave up, where it is concave down. As you can see, your f double prime is negative on this interval. That means your function has to be concave down in this interval. F is concave down on minus infinity comma 0. F is concave up on the interval 0 comma plus infinity. Okay, by the previous theorem. All right, that completes that part, but don't forget we had the second part. Okay, then determine any inflection points. Okay, now let's determine the inflection points for this first part. What are the inflection points? Inflection point, as I mentioned when I introduced the inflection points are the points where your f double prime changes the sign, right? As you can see here is the sign chart for f double prime. It doesn't change the sign. See, plus, plus, the sign is not changed there. That means this function has no inflection points. F has no inflection points. Because if you look at the sign chart for f double prime, you don't find any point where f double prime changes the sign. So no inflection point. What about the next one? As you can see here, this is the sign chart for g double prime. Okay? And as you can see, now you have a point where g double prime changes the sign, minus to positive. Okay, g double prime changes the sign from minus to positive. So that means at this point, we have an inflection point. Okay, f has an inflection point. At x is equal to 0. Okay. All right, that completes that example. Let's move on. Okay, next we have the second derivative test. This is also very important theorem in curve sketching. As I mentioned, the importance of the second derivative test is that we can obtain more detailed graph, okay, shape of a more detailed graph of a function if you know the second derivative test. Okay. All right, here is the statement of the second derivative test. Suppose x is equal to c is the location of a critical point of a function with f prime of c is equal to 0. And suppose both f and f prime are differentiable and f double prime is continuous on an interval around x is equal to c. Then here is the conclusion statement. If f double prime of c is positive, then f has a local minimum at x is equal to c. If f double prime of c is negative, then f has a local maximum at x is equal to c. And if f double prime of c is 0, then test says nothing about whether or not f has an extremum at x is equal to c. Okay. Okay, what the third part tells you is that if f double prime of c is 0, you cannot say whether you are going to have a local maximum or local minimum. Anything could happen. Okay, all right. All right, let's move on. This is the second derivative test. Let's look at some examples. Let's look at some applications of the second derivative test. Okay, notice that again, to apply the second derivative test, we need to find critical points of a function f with f prime of x is 0. So to apply the second derivative test, you need to find the critical points with f prime of x is equal to 0. That means you have to set f prime of x to 0 to find such critical point. Okay. All right. Let's work on this example. Determine local extrema of the function. Okay. Here is the given function f of x is equal to x to the power 3 minus x squared plus 2 using the first derivative test. We need to determine the local extrema of the function using the first derivative test and then using the second derivative test. Let's first focus on the first part. Let's try to find the local extrema using the first derivative test. Okay, for that, remember to apply the first derivative test, we need to construct a sign chart for f prime. To apply the first derivative test, I want to know where my function f is increasing, where it is decreasing. Okay, that means I want to know where my f prime is positive, where my f prime is negative. For that, I'm going to construct a sign chart for my f prime. Well, if you compute f prime, this is what you're going to get. Okay, so let's find the critical points of my f prime, or the zeros of this function f prime of x. By the way, here, the critical points of these functions are the points where your f prime of x is 0, okay, because this function is continuous everywhere. Set f prime of x to 0. You get 3x squared minus 2x is equal to 0. If you pull out an x, you get 3x minus 2 is equal to 0. You get x is equal to 0 or x is equal to 2 over 3. So I'm going to place those numbers here on the number line. 0, this is 2 over 3. Now, to figure out the sign, in this region, I'm going to pick a number in this interval. I'll pick minus 1. If you plug in minus 1 in your derivative function, you will get plus 5. That means the sign in this region is positive. And then in this region, I'm going to pick 1/2. 1/2 is in this region. It's clear. So if you plug in 1/2, you get minus 1/4. That means the sign is negative. And if you go to the last interval, and if you pick a number from this interval, I'll pick 1. And f prime of 1 is going to be 1, which is positive. So the sign is positive. So I have the sign chart. Here, my slope is positive. That means your function should look like this. On the other interval, on the next interval, your function f prime is negative. That means your function should look like this. It should be decreasing. And on the last interval, it should look like this. Okay. This kind of notice that at these points, your function is continuous. Actually, your function is continuous everywhere. So we can apply the first derivative test. You are going to have a local maximum at x is equal to 0 and a local minimum at x is equal to 2 over 3. Okay, we can apply the first derivative test here. All right, now let me write by first derivative test. By first derivative test, f has a local maximum at x is equal to 0 and f has a local minimum at x is equal to 2 over 3. That's by second derivative, because to the left of 0, your derivative is positive. To the right of 0, your derivative is negative. And at 0, and this function is continuous everywhere, so we can apply the first derivative test. So you are going to have a local maximum at x is equal to 0. Similarly here, to the left of this point, your derivative is negative. To the right of that point, derivative is positive. So you are going to have a shape like this, the shape of a local minimum. All right, that is using the first derivative test. Okay, now let's do this using the second derivative test. To do this using the second derivative test, I'm going to have to find my second derivative. F double prime of x, you just differentiate this function one more time, then you get 6x minus 2. That's the second derivative. Okay. Now, how to use the second derivative test? Let's go back and look at the second derivative test one more time. Here is the statement of the test. We found all points C such that f prime of C is equal to 0. We found the critical points such that f prime of C is equal to 0. Those critical points are these. X is equal to 0 and x is equal to 2 over 3. Now we go with those critical points for the remaining part of the theorem. Here is the first part. If f double prime of C is positive, then f has a local minimum at x is equal to C. So to determine what kind of a local extrema we have at x is equal to 0, I have to plug in x is equal to 0 in my second derivative function. And if the sign, if that is positive, then I'm going to have a local minimum at that point. And if f double prime of C is negative, then I'm going to have a local maximum at that. So let's plug in this point. I copied my content to the next page, and let's plug in those critical points in the f double prime. F double prime of 0 is equal to minus 2, which is negative. Now I can apply the second derivative test. Okay, what does the second derivative test tell you? If f double prime of C is positive, then f has a local minimum at x is equal to C. If f double prime of C is negative, then f has a local maximum at x is equal to C. So that means here f double prime of 0 is negative. So I'm going to have a local maximum. Local maximum at x is equal to 0. And then let's check the other critical point, 2 over 3. F double prime of 2 over 3 is equal to, you compute that if you plug in 2 over 3 in this function, 6 times 2 over 3 minus 2, which will be equal to 1. Pardon me, it is 2. Okay, so that is positive. That means again by the second derivative test. By second derivative test, STD, f has a local minimum at x is equal to 2 over 3. Okay, and here also you may write by second derivative test, local maximum is at x is equal to 0. All right, that completes that example. Notice that in both methods, we came up with the same answer. Using the first derivative test, we determined that f has a local maximum at x is equal to 0 and local minimum at x is equal to 2 over 3. Even from the second derivative test, we determined that local max at x is equal to 0 and local mean at x is equal to 2 over 3. Okay. All right, let's move on. Okay, next, let's see how we can use this second derivative test idea to get a graph of a function with more details than that we obtained from the first derivative test. All right, so let's look at this example. Use derivatives, algebra, and sign charts to sketch the graph of f of x is equal to x to the power 5 minus 15x cubed. Identify the coordinates of each root, local extremum, and inflection points. Okay. All right, so what I'm going to do is, first of all, I'm going to construct a sign chart for my f of x. Okay, because clearly it asks us to find the roots of coordinates of each root. So I'm going to have a sign chart for my f, and then I need to identify local extrema. To identify my local extrema, I can use the first derivative test. So I'm going to have a sign chart for f prime. Okay. And then to identify inflection points, I'm going to have a sign chart for f double prime. Okay. So first of all, let's observe that this is the given function. Let's look at the sign chart for f first, f of x. This is the given function. You pull out x cube, and you get this factorization. And then you can factorize this again. This is x squared minus 15. You can view that as x squared minus square root of 15 squared. Now, this is the difference of two squares. So the factors of this expression would be x minus square root of 15, x plus square root of 15. So you get the complete factorization of this. Now, how do you find the zeros of this function f of x, or roots of that function? Roots and zeros are the synonyms, okay? They are the same. So how do you find the zeros of this function, or roots? Roots of f of x would be, all what you do is you set each individual factor to 0 in this factorization. You set this part to 0, this part to 0, and this part to 0. If you set this part to 0, you get x is equal to 0. That's your first root. The second root, or second zero, would be x is equal to plus square root of 15. The last one would be x is equal to minus square root of 15. Okay, so I'm going to place those numbers on the real number line for f. This is minus square root of 15, 0, 15. Now, to construct my sign chart, I can pick a number from each interval. I pick a number from this interval. Let's say, for example, minus 6. You plug in that minus 6 in your function. Then you will see that you get a negative number. So you put a negative sign here, and then you pick a number from this interval, plug in that number in your function f, you will see that your sign is positive, and you pick up number from this interval, plug in that number in your function f, you will see that that is negative, and here it is positive. So this is the sign chart for f. And then you need to construct a sign chart for f prime to find local extrema. Okay, so here is your f prime. If you differentiate this function, this given function, this is f prime of x. Similarly, we factorize this expression completely. Here is the complete factorization. You can find the roots of this function. Roots or zeros, okay? They are the same. X is equal to 0, x is equal to 3, x is equal to minus 3. Those are the zeros. Now, let me place those zeros on the number line. Minus 3, 0, 3. Now, similarly, as I did for the case f of x, I am picking a number from each of these interval and plug in that number in my second derivative function. I pick a number from this interval, say for example, minus 4. You plug in that number in the first derivative function, f prime of x, and determine the sign. You will see that it's going to be a positive sign. Similarly, by picking a number from each interval, you can determine the sign in that interval. Okay, you will get these signs: plus, minus, minus, plus. Okay, next, I want a sign chart for f double prime. Okay, first of all, to construct the sign chart, I need the roots of my f double prime. Notice that in all these three cases, all these are polynomials. Polynomials are continuous everywhere. So it can change the sign only at its zeros, if it does. So that's why I'm finding zeros, okay? This is where f can change the sign if it does. And this is where f prime can change the sign if it does. And the roots of f double prime will give you the places where f double prime can change the sign. So what are the roots? X is equal to 0, again a root. You get x is equal to 3 over square root of 2. And you get x is equal to minus 3 over square root of 2. Now I am placing these three numbers on the number line over here. Minus 3 over square root of 2, 0, 3 over square root of 2. Similarly, I do I do the same thing that we did in the that I did in the previous parts. I pick a number from this interval, plug that in my second derivative. You will see that the sign is negative. In this interval, you will see that sign is positive. In this interval, sign is negative. In this interval, sign is positive. So I have the complete sign charts for all the three functions: f, f prime, f double prime. Okay, that's all we need to get the shape of the graph. Okay, now with that in my mind, let's explore a few things here. So this sign chart tells you that these are the zeros of your function. Okay, so here in this interval, your function has to be negative. That means your function has to be below the x-axis. And in the next interval, your function has to be above the x-axis because sign is positive. It could be like this. And then this is a 0 again. You have to come and touch or cross the x-axis. In the next interval, in the interval 0, square root of 15, your function is negative. You have a negative sign there. That means it should stay below. And then here again, it is a 0. And then on the last interval, your function has to be positive. Sign is positive. So we would expect a graph like this. But we need to be careful. Okay, because according to this f prime, we have a 0 at -3. That means at -3, first of all, notice that at -3, we can use f prime to determine the local extrema. For example, here you have positive slope. That means the shape is like this. In this interval, shape is like this because you have a negative slope. Here again, you have this shape because you have a negative slope. On the other interval, you have a graph like this. Okay, all right. So we can use this sign chart for the first derivative to determine the local extrema. As you can see here, notice that my f is continuous and differentiable everywhere. So it is continuous at x is equal to -3. So you should have, by first derivative test, you should have a local maximum at x is equal to -3. And by the first derivative test again, you have a local minimum at x is equal to 3 here. Okay. And here, it does not change the sign. Okay. Your sign is not changed here. So you are not going to have a local extrema at this point at x is equal to 0. And the f double prime, sign chart for f double prime tells you where your function is concave up and where it is concave down. Okay, here in this interval, your function is concave down. In this interval, it is concave up. In this interval, it is concave down. And in the last interval, it is concave up. And we also can get some information about the inflection points by looking at this sign chart for f double prime. Notice that inflection points are the points where f double prime changes the sign. So the inflection points are what are the points where f double prime changes the sign? Here, clearly f double prime changes the sign. Minus, plus, sign is changed. At this point also, sign is changed, plus, minus. At this point, again, sign is changed, plus, minus. We have 3 inflection points. X is equal to -3 over square root of 2, 0, and 3 over square root of 2. Those are the 3 inflection points. That means at these points, my concavity changes. Okay. Here, let me write by first derivative test, local maximum at x is equal to -3 and local minimum at x is equal to +3. As you can see here you have a local maximum because to the left of -3, your slope is positive, f prime is positive. To the right of -3 in this interval, your f prime is negative. So that means by first derivative test, you have a local maximum. Clearly here again, by first derivative test, you have a local minimum at x is equal to 3. All right, at x is equal to 0, we don't have a local extreme because both derivative in both sides are going to be negative. Okay, with these details in our hand, let's try to draw the graph of my function. All right, here I copied some of the stuff from the last slide here. I have the information of local extrema here, and here are the inflection points. The next thing I do is I place all these points on the x-axis. First of all, I create my y-axis and the x-axis for my graph. I'm going to draw my graph on this xy plane. I'm going to place all these involved numbers on the x-axis. Okay, if I place all those numbers, these are those numbers. Now I know that at x is equal to -3, I have a local maximum. I determine that using the first derivative test. Now I can find the maximum value by plugging this number in my function. If I plug in x is equal to -3 in my function, you will get 162.000. Okay, so my y value is, or the minimum value, the maximum value, pardon me, is going to be 162. I know that my shape is going to look like this. Okay. All right. And again, here at x is equal to 3, we know that we have a local minimum. And of course, I can find that minimum value by plugging x is equal to 3 in my function. That will be minus 162.000. That is, value is here. So that means my graph passes through this point and it should have this shape here. Here it is like this, local maximum. Here it is like this, local minimum. Okay. And also these are the inflection points, this point, and this point. And of course, I can plug in the function value at this point by plugging this number in my function. So that value would be 100.232. Similarly, by plugging this point, we will get the desired y value. And these are the inflection points. That means your function changes the concavity. Okay. All right. Now I located these points. I have located these 3 points are zeros. I know that. I already know that those are zeros of your function. So I have placed those 3 points and I found the other remaining 4 points on the graph, because this is the maximum point. And this is the y value corresponding to your first inflection point at x is equal to -3/√2. And here is the y value when x is equal to 0. And here is the y value when x is equal to 3/√2. Now I'm ready to graph. Okay, notice that when I graph on this interval, if you look at f prime, on this interval, my function is increasing. So your graph should look like this. The function should be increasing up to that point. And at x is equal to -3, your derivative is 0. So that means you should have a horizontal tangent. And then in the interval -3, 0, your function should be decreasing. It should be going down like this. But notice that at this point, your function should change the concavity. It should be like this up to here. And then after that, it changes the concavity like this. And notice that at x is equal to 0, I have an inflection point. That means, again, it changes the concavity. Okay. And then goes like this. Here again, it is changing the concavity. And here, of course, your derivative is 0 at x is equal to 3. And then it is increasing beyond 3, because beyond 3, f prime is positive. Okay. So your graph should look like this. Okay, again, at this point, you have the local maximum. And in this region, your function is increasing. That looks good. And then it's coming like this. And at this point, it changes the concavity. In this region, your function, the concavity looks like this. And after that, it becomes like this. Concave up. Here it is concave down. In this region, it is concave down. Here it is concave up. Again, here it changes the concavity. Here it is concave up. In this region, it is concave down. Again, here function changes the concavity. In this region, your graph looks like this. That is concave up. Here it is concave down. Okay. So we have all those properties on this graph. Let me make it a little bit smoother here. So here is the graph that you have at the end of the day, okay, with all these properties. All right, that completes that example. Let's move on. Okay, the next example that I want to work on, this particular example, sketch an accurate label graph of the function f of x is equal to x over 1 plus x squared. Include complete sign analysis of f, f prime, f double prime, and calculate any relevant limits. Okay. All right, let's work on this one. Again, the procedure is same. I'm going to construct a sign chart for my f, sign chart for my f prime, and sign chart for my f double prime. Okay, here is my f of x. Of course, to construct a sign chart for my f of x, I need to find the points where f of x can change the sign. Okay, here notice that this function is defined everywhere because you have 1 plus x squared in the bottom, which this is positive. This is always positive. There are no points where f is not defined. Okay, f is defined for all x values. So this can change the sign only at its zeros. The zero of f of x is 0 of f, I would say f, is x is equal to 0. What do? You set your numerator to 0 to find zeros. That is x is equal to 0. So I place my x is equal to 0 here. And then I construct the sign chart for my f. What do? I pick a number from this side and plug in that number in my function. You will see that the function value is negative. If you plug in a number from this side in your function, you will see that your function value is positive. And then we can calculate the derivative of this one. To construct the sign chart for the derivative, f prime of x is going to be 1 minus x squared divided by 1 plus x squared whole thing squared. This is your f prime of x. I'm not going to do the calculation. You can, of course, use the quotient rule to find the derivative of f of x. You will see that the derivative is going to be this one. Okay. Now I'm going to have to construct a sign chart for the derivative. For that, again, I'm going to find the zeros of my derivative, zeros of f prime. Because my f prime can change the sign only at zeros because there are no points where the function is undefined or discontinuous. So zeros of this function, to find zeros of this function, what do? You set your top to 0. 1 minus x squared is equal to 0. That will give you x is equal to plus or minus 1. You have two zeros, plus 1 and minus 1. I place those two zeros, minus 1 and plus 1, and then construct the sign chart. I pick a number from this interval, plug in that number in my derivative function, and figure out the sign. That sign will be negative if you plug in a number. Okay. Similarly, on this interval, it is positive. In this interval, it is negative. And then I calculate my f double prime, the second derivative. You differentiate this function one more time to get the second derivative. Now I find the zeros of the second derivative. Notice that my second derivative function is also can change the sign only at its zeros because this function is continuous everywhere. Zeros would be, you get x is equal to 0 and you get x squared minus 3 is equal to 0. This is x is equal to 0 and you get x is equal to plus or minus square root of 3. If you move this 3 to the other side and take the square root, you get plus or minus square root of 3. So I have three zeros for f double prime. Minus square root of 3, 0, square root of 3. That means I have the sign chart for my function f. Okay. All I have to do now is to draw the graph using the information that I obtained from this sign chart. Let's notice few things here. First of all, to the left of 0, my function has to be negative. That means it should be below the x-axis, and to the right of 0, my function has to be above the x-axis. But what about the end behavior? Would it go like this, or would it show a behavior like this? Well, if you look at this function, I can easily determine the horizontal asymptotes. Notice that the degree of the top expression is 1, the degree of the bottom expression is 2. 2 is bigger than 1. That means your horizontal asymptote of this function is y is equal to 0. Horizontal asymptote is y is equal to 0. Okay, so horizontal asymptote is y is equal to 0. That's the horizontal asymptote. And also notice that at these points, if you look at f double prime of x, sign chart for f double prime of x, f double prime is negative in this region. That means your function is concave down in that region. Here f double prime is positive. That means your function is concave up. Double prime is negative, concave down, and if double prime is positive, it is concave up in this interval. Okay, and also at these points, notice that your f double prime changes the sign. That means these are inflection points. Okay, inflection points are x is equal to minus square root of 3, 0, and square root of 3. Those are the 3 inflection points. Okay, and notice here that I can use this sign chart for the f prime to find the local extrema. As you can see here, the function is decreasing because your f prime is negative. Here it should be increasing. F prime is positive. In this region, function should be decreasing because f prime is negative in this region. Okay, so it is decreasing in this region. F is increasing in this region. F is decreasing. Now I can apply the first derivative test. To the left of this number, it is decreasing. F prime is negative. To the right of -1 in an interval, your f prime is positive, or your function is increasing. That means by first derivative test, I'm going to have a local minimum at x is equal to -1. Notice that my function is continuous everywhere. Okay, so I can apply the first derivative test. By first derivative test, f has a local minimum at x is equal to -1 and local max at x is equal to +1. Notice that here at x is equal to +1, you have a local maximum because the derivative is positive to the left of 1 and derivative is positive to the right of 1. You have a shape like this. The shape itself suggests you the shape. Okay, it should be a local maximum. Okay, now keeping these features in mind, now we can draw the graph. Notice that our horizontal asymptote is y is equal to 0. Now let's go to the xy plane. All right, let's proceed. Now we can, one thing that we can do is we can find the local minimum value by plugging x is equal to -1 in my function. Okay, my function is x over 1 plus x squared. If I plug in -1 there, we can find that f of -1 is equal to -1/2. I can find the local maximum at x is equal to 1 by plugging x is equal to 1 in my function. If you plug in x is equal to 1, you will get f of 1 is equal to +1. So I have the value of the local minimum and the value of the local maximum. That means this point has to be on my graph -1, -1/2, and here 1, 1/2. The local maximum is at this point, it is 1, 1/2. Here it is -1, -1/2. That's where I have the local minimum. Now I can draw a rough sketch. Local minimum means at this point, you should have a shape like this. And notice that if you look at the sign chart for the second derivative, it is decreasing on this interval. Okay, so that means from minus infinity to -1, it is decreasing. So I have a shape like this. And notice that this is my horizontal asymptote. So my graph should be getting closer and closer to that horizontal asymptote, and it should be decreasing up to -1. And then between -1 and 1, it is increasing because my f prime is positive. So it should be going up. And here again, I'm going to have my local maximum. And of course, my derivative is 0 at x is equal to 1 because this is a 0 of f prime. Okay, so you should have a horizontal tangent there. And then beyond 1, my derivative is negative. Beyond 1, my derivative is negative. Function should be going down. And since y is equal to 0 is a horizontal asymptote, graph should be getting closer and closer to the x-axis. Okay. And also notice that at these points, minus square root of 3, 0, and square root of 3, concavity is changing. Look here. If you look at here, this is concave down shape. And then all of a sudden, it becomes concave up. In this piece, it is concave up. As you can see here, this is a concave down shape. So that means at this point, concavity changes. Here also, at this point, concavity changes because it's an inflection point. As you can see, here it's concave up. In this piece, it is concave down. Okay, so concavity changes here. Here also, again, concavity changes. Here you have a concave down shape. In this piece, you have a concave up shape. Okay, concavity changes because these 3 points are inflection points. Okay, so this completes the graph of f of x using sign charts. And of course, notice that according to this sign chart, in this region, your function f is concave down, is clear. In that region, your function is concave down. And then between minus square root of 3 and 0, it is concave up, is clear again, is concave up in this region. And on this region, again, it is concave up between 0 and plus square root of 3. And beyond plus square root of 3, it is concave up. This is concave down, by the way. Here it is concave down. Here it is concave up. All right, that completes the last example that I wanted to go over. All right, I'll stop there and I'll see you next time.